Now, what we will do is we would like to go through the paper and discuss the key tables here. The paper that we are dealing with is entitled Choosing Factors from Fama and French, 2018, published in the Journal of Financial Economics. So we discussed already what's the problem. So the problem is that we have about more than 316 anomalies that are proposed in the literature as potential risk factors in asset pricing models. And now the question arises, how can we choose, or what should be the criterion how to choose among these factors? Which of these factors are potential candidates for risk factor models or for asset pricing models? So we discussed also that previous literature adopted the so-called left-hand side approach, and the novel aspect in the paper from Fama and French is that they propose a so-called right-hand side approach that uses spanning regressions to judge which individual factors are potential candidates as risk factors. So the model that you see here in equation 4, that's the basic model, the 6-factor model that we are dealing with. We see on the left-hand side the return of portfolio I at time t minus the risk-free rate at time t is regressed on a constant, the intercept term alpha or r in this equation, e or ri. I denotes the portfolio or the asset, plus b I times the market factor in excess form plus exposure Si against the size factor plus Hi times the value factor plus Ri times the profitability factor, and we see O, this O denotes operating profitability, plus Ci times the investment factor plus Mi times the momentum factor. And because it's a regression equation, we also add a residual term captured by this EIT, okay, which is the residual of asset I at time t. So we can directly go to the table number 1. In table number 1, panel A, we see that the market factor in excess form generates a payoff of 0.50% per month. The corresponding t statistic you see here on the right-hand side is 2.84, which indicates that the market factor is significant on a 5% level, right? Because it exceeds the critical value of 1.96. Also, the size factor, what we see here, size factor generates an average payoff of 26 basis points per month or 0.26% per month, with the corresponding t statistic of 2.17, indicating significance on a standard 5% significance level, because the t statistic of 2.17 exceeds the critical value of 1.96. What we see here in panel B, we have the summary statistics for the value factor, operating profitability factor, cash profitability factor, investment factor, and momentum factor. Yeah. Let's just focus here on the first 3 rows. What we see here is that the value factor generates over the sample period, which is from what you see here, from July 1936 until June 2016, an average payoff of 35 basis points per month with a t statistic of 3.15, indicating also significance on any level, because 3.15 is obviously much, much larger than the critical value of 1.96. The profitability factor, RMW, which is here, generates an average payoff of 0.24% per month or 24 basis points per month with a t statistic of 2.75, also indicating significance on any level. The profitability factor using cash profitability, this is the profitability factor using operating profitability, and here next to it on the right hand side we have the corresponding profitability factor using cash profitability. The payoff is slightly higher. It's 0.36% per month, or 36 basis points per month, with a corresponding T statistic of 4.71, indicating significance on any level. What we see now already is that the economic magnitude of the profitability factor using cash profitability is about 50% higher than the corresponding profitability factor using operating profitability. The economic magnitude is 0.36 compared to 0.24, and also the significance level is much higher, because the T statistic is 4.71 using cash profitability against 2.75 for the profitability factor based on operating profitability. The investment factor, the standard investment factor denoted as CMA, here generates an average payoff of 0.31% per month with a corresponding T statistic of 3.88, also significant on any level. The same is for the momentum factor, which has the in economic magnitude generates the highest payoff of 0.69% per month, or 69 basis points per month, with a T statistic of 4.09, indicating significance on any level. In the next row here, what we see here, you see the corresponding factor spreads using small stocks only. So what we see here is if you use just these small stocks and implement the value factor among the small stock universe, we see that the payoff is much higher compared to the whole universe of stocks. We have an average payoff of 0.51% per month with a T statistic of 4, indicating significance on any level. And the same is true if you go through all of these factors here. If we use small stocks and implement the corresponding risk factors here, irrespective of which risk factor we consider, all of these risk factors here have higher average returns. And most of them have also higher T statistics, apart from the profitability factor using operating profitability. If we use big stocks, what we see here in the third row, using big stocks, obviously the payoff of all of these risk factors here is relatively small. And only the payoffs for cash profitability, for the investment factor, and for the momentum factor, only those guys here, they have T statistics that indicate statistical significance on a 5% level, on at least a 5% level. So that's basically the important thing to know from table 1. So let's go to table 2. Table 2 is entitled Spanning Tests for Nested Models. Sample period is of course the same like in the previous table, from July 63 until June 2016. What we see here is, as we discussed in the lectures, so we test different asset pricing models against each other. And here we are dealing with nested models. So what we see here is, in the first 2 rows here, we regress. We have on the left-hand side the size factor denoted as SMB and the value factor denoted as HML. And we regress these 2 risk factors on an intercept term and the market factor. So what we see here is, okay, what we test is the Fama and French 3-factor model against the CAP-M. Because the 3-factor model nests the CAP-M model. The 2 additional risk factors of the 3-factor model that are not included in the CAPM model are the size factor and the value factor. And we regress those additional risk factors that are not included in the CAPM on the CAPM. This is what happens here. So the intercept term of the first regression equation is 0.17. So 17% of the excess returns of the SMB factor remain unexplained by its exposures against the market factor. But the T statistic, what we see here on the left-hand side, on the right-hand side, is 1.46. So it indicates that this 0.17, this intercept term, so the part that is unexplained from the CAPM, is not significant on the 5% level. So we cannot say that the size factor is unexplained by the CAPM. But as we know, this is a simultaneous equation model. So we have to estimate this model by seemingly unrated regression technique. The second equation, in the second equation, we regress the value factor on the CAPM. Okay, what we see here is the payoff is the unexplained payoff of the value factor is 0.43% per month. So this is the part unexplained by the exposure against the market factor. And we see that the T statistic of the intercept term is 4.01 and indicates significance on any level. So if we now test these two parameters simultaneously, what do you think what will come out? The first guy is insignificant, but the second intercept term is significant, highly significant. So we test under the null hypothesis that both should be 0 against the alternative hypothesis that either one of these or both are unequal to 0. We know now already that at least the second one is unequal to 0, so our intuition would obviously tell us that if we test those point estimates simultaneously here, then the test should indicate that we reject the CAPM and we accept the alternative hypothesis, which is the three-factor model, because at least one of these guys here is significant. And this is exactly what happens here in panel B, multi-factor tests. So under the null hypothesis, the null model is the CAPM, yeah, and the alternative model is the three-factor model. So testing those two guys here, these two intercept terms simultaneously results in a test statistic, which is the GRS test of 9.20. And the corresponding p-value is 0.00, yeah? which indicates that we reject the null hypothesis, and the null model is the CAPM, so we reject the CAPM, and we accept the alternative hypothesis. So under the alternative hypothesis, the three-factor model is the corresponding asset pricing model. In other words, the CAPM cannot explain these two additional risk factors of the three-factor model simultaneously, which means that adding these two risk factors here, the size and the value factor, to the CAPM results in an increase or in an expansion of the mean variance frontier. Yeah? This is what it means. Under the null hypothesis, because we have two intercept terms that we test, and during the lectures, we discussed that under the null hypothesis, the corresponding test statistic is distributed as chi-square distribution with 2 degrees of freedom. Now, there are different possibilities to implement the GRS test. So usually what you can use is the chi-square distribution, in this case with 2 degrees of freedom, because we have two intercept terms that we test. But in other papers, they use the F test. And obviously the F test and the chi-square test are basically, they do the same thing. So you can basically calculate the T test or the F test using the chi-square test statistic and vice versa. So what happens here next? So what happens here next is what you see here is we test different versions of the 5-factor model against the 3-factor model. Now under the null hypothesis here, we have the three-factor model. Yeah, so the market factor, the size factor, and the value factor. We have here a regression equation where we regress the operating profitability factor on the three-factor model. And what you see here is in this row the corresponding point estimates. We are interested mostly in the intercept term 0.33, 0.34. The corresponding t-statistic is 4.01, indicating significance on any level. The second regression equation, we regress the cash profitability factor on the three-factor model. Yeah, here you see the point estimates. Most importantly here, the intercept term is 0.48% per month. Yeah, remain unexplained by exposures against the three-factor model. We see that this intercept term is highly significant. The corresponding t-statistic is 7.88, much larger than 1.96. Yeah, so significant on any level. In this regression equation here, we regress the investment factor CMA on the three-factor model. Again, 0.20% per month is the part unexplained by exposures against the three-factor model. The t-statistic of this intercept term of 0.20 is 3.53, also indicating significance on any level. So what we do then is, okay, we test the three-factor model using first operating profitability, which means, okay, under the null hypothesis, we have the three-factor model, and under the having the market factor in excess form, size factor and value factor, and under the alternative model, we have the five-factor model, yeah, which has the, like in the three-factor model, the excess market factor, the size factor, the value factor, and in additional two more regressors or two more risk factors, which is the profitability factor using operating profitability and the investment factor. Yeah, since we have, it's again a test using nested models, so we only have to test on the left-hand side. We have the two risk factors that are included in the five-factor model, but that are not included in the three-factor model. And these two additional regressors or risk factors are these guys here. So again, we have a simultaneously equation model using seemingly unrelated regression technique. Okay, in other words, we test this guy here, 0.34 and 0.20. Yeah, we using these two regression equations here and test these two intercept terms simultaneously if they are simultaneously different from zero. Yeah, we know already from the t-statistics here that both guys are indicated significance on any level, and this is also what we see here. If we do the simultaneous test, the test statistic is 17.99. Yeah, the p-value is 0. Yeah, so which means that we reject the three-factor model and accept the alternative model, and under the alternative we have the five-factor model, which means that these two additional risk factors using operating profitability and investment, they expand the mean variance frontier. So if we add those to the three-factor model, we have a higher Sharpe ratio of the optimal portfolio. So we would choose this five-factor model against the three-factor model. What we see then here in the last row, yeah, we do a simultaneous test using the equation, this equation here, where we have on the left-hand side the profitability factor using cash profitability and the investment factor. Okay, we regress these two risk factors on the three-factor model, and we test these two intercept terms here, 0.48 and 0.20, simultaneously. Again, using a seemingly unrelated regression framework and then implementing a chi-square test of these two point estimates simultaneously. Yeah. So again, under the null hypothesis, we have the three-factor model. Under the alternative hypothesis, we have the five-factor model. Yeah, we have using this test for nested models. Those two risk factors that are included in the 5-factor model but not included in the 3-factor model. These two additional risk factors is the investment factor and the profitability factor, here in this case using cash profitability. So what we see is the GRS test is 37.46, yeah, highly significant, p-value of 0, yeah, whenever the p-value is below 0.05 means that we reject the null hypothesis, implying that the test statistic indicates significance on a 5% level. Again, the same conclusion. The 3-factor model cannot price these two additional risk factors of the 5-factor model, which are the investment factor and the profitability factor, in this case using cash profitability, implying that we reject the 3-factor model and we accept the 5-factor model, in this case using investment factor and the profitability factor using cash profitability as additional risk factors. Again, using these two additional risk factors, expand the mean variance frontier. Last but not least, in the last two rows here, or what we see here is they regress the momentum factor on the 5-factor model, either using operating profitability as a regressor or using cash profitability here in the last equation as a regressor. But whatever you use, you have the same conclusion, because what we see is that the intercept terms of 0.73 or 0.61 are statistically significant. What you see here is on the right-hand side, because the t-statistic of 4.34 and 3.55 are much higher than 1.96, yeah? So indicating that these guys here are significant, irrespective of which type of probability factor you use in your model. And in this case, under the null hypothesis, we have the 5-factor model, yeah, incorporating the market factor in excess form, size factor, value factor, one of the probability factors, and the investment factor. And under the alternative hypothesis, we have the 6-factor model, adding only one factor, which is the momentum factor. If you implement now a test for nested models, we know that we have only one additional regressor in the 6-factor model, which is the momentum factor. Yeah. So what we do is the only test or the corresponding test statistic that we are interested in is the simple t-test. Okay, because we have only one additional factor. And based upon the t-test, we see, okay, adding the momentum factor to the 5-factor model adds or expands the mean variance frontier, because the t-statistic indicates that the momentum factor cannot be fully explained by exposures against these 5 factors here, because the intercept term, we have here a remaining part of the zero cost portfolio returns that are significant, yeah, that remain unexplained. So that's basically what we learn from table 2. So again, whenever the intercept term is significant, it means that this risk factor, adding this risk factor or adding these risk factors towards an existing model increases the mean variance frontier, which means that it increases the maximum squared Sharpe ratio. The question arises, how do we evaluate models that are non-nested? Non-nested models are obviously models that have at least one regressor that is different from each other, right? So here, what we see is in table 3, the table description, comparison of 6-factor models that include an operating profitability or a cash profitability factor. So we have here obviously two different main models. And let's have a look here on the first row. We have here the market factor in excess form, size factor, value factor, profitability factor using operating profitability here, the investment factor and the momentum factor. Yeah, this is the standard 6-factor model that you also have encountered in equation 4, right? Isn't it so? Using the actual data set, again, the data set runs from its monthly data from July 63 until June 2016. Using actual data, these 6 risk factors here generate a maximum squared Sharpe ratio of 0.135. 0.135. The 6-factor model using cash profitability instead of operating profitability, which we see here in this row here, has a higher maximum squared Sharpe ratio of 0.19. 0.19 is larger than 0.135. What we see here is, if we, let me just go on. So what we see here is, if we do a full sample simulation, which means that we draw with replacement from this whole sample and create 100,000 artificial samples. Okay? And then we again estimate the maximum squared Sharpe ratio for this factor model, the 6-factor model using operating profitability, and the 6-factor model here using cash profitability. Yeah, we average the maximum squared Sharpe ratio across these 100,000 samples, full sample simulations. What we get is an average maximum squared Sharpe ratio of 0.152 using the 6-factor model with operating profitability against 0.28, 0.20 and 8 as a third digit using the 6-factor model with cash profitability. So what we see here is, irrespective of if we use the actual data or if we use the simulated data using the full sample, we always get a higher maximum squared Sharpe ratio when we use a 6-factor model that uses cash profitability instead. Here, what we see here is in the second line, we see a 6-factor model that uses the excess market factor, size factor, and small spread risk factors. For the value factor, small spread. We use just small stocks and implement the value factor. Here we have the profitability factor using operating profitability and only small stocks. Here, the investment factor using only small stocks and the momentum factor using only small stocks. Here, below, you see the 6-factor model also based upon small stocks for the value, profitability factor, investment factor, and momentum factor, but using, instead of operating profitability, cash profitability. We see here for the actual data, the Sharpe ratio of 0.226 of this model here is larger than the Sharpe ratio of this model here using operating profitability and small stocks, which is 0.199. Again, if we do the simulation, the full sample simulation, building 100,000 artificial data sets, by drawing each factor, randomly with replacement from the original data set, creating 100,000 samples, and then averaging the maximum squared Sharpe ratio across the samples. What we see is here we have, for the 6-factor model based upon small stocks and operating profitability, a average Sharpe ratio of 0.217 against 0.244 if we use small stocks and cash profitability. So the same result, basically, using cash profitability generates a higher maximum squared Sharpe ratio if we use this factor in the 6-factor model. The same is true for the median. Okay. We also discussed in-sample and out-of-sample simulations. So we have here the in-sample, the corresponding in-sample maximum squared sharp ratios, and here on the right-hand side, the out-of-sample maximum squared sharp ratios. So what we see is that the out-of-sample maximum squared sharp ratios is always lower compared to the in-sample maximum squared sharp ratios. But if we compare here the out-of-sample maximum squared sharp ratios of the six-factor model using cash profitability, either using all stocks or small stocks, we see that the sharp ratios here of 0.159 is higher than 0.108 and 0.194 is higher than 0.169. So also if we use the out-of-sample simulation, the results are the same. We would prefer a six-factor model using cash profitability, and moreover, we would prefer a six-factor model using cash profitability and association with small stocks for implementing the value factor, profitability factor, investment factor, and momentum factor. So this is basically the takeaway or the important finding from table 3 of this paper. If we now move on to table 4, the table description is entitled Distributions of Differences Between the Maximum Squared Sharp Ratios, Column Model minus Row Model. So what do we learn from this table? So this is the basic model here on the left-hand side. So this is the model that we basically test against. So what we see here is the standard model from equation. No, this is not equation 4, but this model here, the six-factor model here uses all stocks, and it includes the market factor in excess form, size factor, value factor, profitability factor using cash profitability, the investment factor, and the momentum factor. And what we see here is, obviously here, the first row here is empty, because we will test this model here, the row model, against the column model here. So obviously this is the same model. So we have to move to row 2, where we test this model here, but using only small stocks. We see here excess market factor, size factor, the value factor using only small stocks, the cash profitability factor using only small stocks, the investment factor using only small stocks, and the momentum factor based upon small stocks. What we see is that if we subtract the maximum or the average maximum squared sharp ratio from this model minus this model here is negative, which means that this model here, this row model here, produces a maximum squared sharp ratio that is 0.031 units higher than the maximum squared sharp ratio of this model here. So if we subtract the sharp ratio from this, the maximum squared sharp ratio from the column model from the row model is obviously then negative. This 91.3% means that this row model here, using small stocks here for compounding these risk factors here, in 91.3% of the 100,000 simulation runs, this row model here generates a higher maximum squared sharp ratio than the column model here. Okay? Which tells us something about the significance, about the statistical significance. Because what we saw here in table, if you go back to table 3, these are just average estimates. From using the actual data or full sample or in and out of sample. So, but we have only a point estimate. These are only point estimates. This can be purely by chance. This can be just a white noise. We don't know. It's just a point estimate. So we need some sort of distribution. And this is what we get here in table 4. So this tells us that in 91% of these runs, of this 100,000 simulation runs, this row model here using small stocks has a higher maximum squared sharp ratio than a column model. So now let's move to column number 4. Here we have the market factor we have as a model that we test. We have the market factor in excess form, size factor, value factor, profitability factor using operating profitability, investment factor, and momentum factor. So we test this model here from equation 4, now you remember, right, against the column model, which is the 6-factor model using instead of cash profitability. So we see that this model here, this column model using cash profitability, has on average 0.056 units higher maximum squared sharp ratio than this model here. Okay, because we subtract the maximum squared sharp ratio again from the column model from the row model. What we also see is that this model here, using the 6-factor model using operating profitability, has in 0% of these 100,000 simulations a higher sharp ratio than this model. So this tells us something about the significance, right? Because in 100% of all simulations, also in all runs, in 100% of the simulations, the color model here outperforms this row model here. This is what this number here tells us. And what we have here we only consider in the upper table here, we only consider full sample simulations. Okay, all of the simulations are full sample simulations. This is also important to know. Next, here in the middle, what we have in the middle is, so we have as model that we use as a benchmark model is the 6-factor model that includes small stock risk factors, risk factors based upon small stocks for implementing the value factor, the profitability factor using cash profitability and small stocks, investment factor using small stocks, and the momentum factor using small stocks. So in the first row, we test the 6-factor model using cash profitability against this 6-factor model, the respective 6-factor model, but based upon small stock spread risk factors. We see that on average, this column model here produces a maximum squared sharp ratio that is on average 0.037 units higher than the sharp ratio of this row model here. Yeah. And we see here that in only 8.7% of this 100,000 simulations, this row model here produces a higher maximum squared sharp ratio than the column model here. So this column model here really outperforms, okay? So again, this 8.7 tells us something about the significance of the difference in maximum squared sharp ratios. So again, what we see here is if we test the column model against the row model here, where we have equation 4, yeah, the standard 6-factor model, but using operating profitability instead, we see that this column model here produces a maximum squared sharp ratio that is 0.093 units higher than the sharp ratio of this model here. And in 0% of this 100,000 simulation runs, this model outperform this model here. So this model here is really, really superior. This is what we learn from this table. Okay? If we move down here, we can do the same thing for the in-sample simulations. And here in the lower part of the table, you see basically the corresponding figures for what happens then in the out-of-sample simulations. Yeah, and the numbers are slightly worse, but they basically confirm what we see here, what we learn here from the full sample simulation. So the best model is to use would be, we would select basically this model here that uses the 6-factor model that uses cash profitability first and also small stocks for implementing the value factor, the profitability factor, investment factor, and the momentum factor. Yeah, this is the model that basically outperforms. Spread factors based on small stocks are better than standard spread factors. Let's now move to table 5. So in table 5, basically, it's entitled Spanning Regressions and Marginal Contributions to the Maximum Squared Sharp Ratio for 3 models that produce the highest maximum squared sharp ratio in table 4. Okay. So basically, what is this table about? So we regress here on the left-hand side. So we regress in the first row the market factor in excess form on these risk factors here. So we regress the market factor on all of the other risk factors. Yeah. So we see this, obviously this entry here is 0 because we would not regress what is on the left hand side on the right hand side. Okay. So we regress the market factor on what? On the size factor, on the value factor, on the profitability factor using cash profitability, on the investment factor, and on the momentum factor. These are the point estimates here, and what you see here is the t-statistic for the R, for the alpha, which is 0.04, which means that 1.04% per month of the market factor cannot be explained by exposures against the remaining 5 factors of the 6-factor model. Okay, the t-statistic is 6.77. So including the market factor increases the mean variance frontier. We see also here that these remaining 5 risk factors, they explain 31%. Yeah, which is the R squared. 31% of the variation of the left-hand side return, which is the market factor. So the market factor is obviously very important. And what we see here is from the table description, the each factor's marginal contribution to a model's maximum squared sharp ratio, which is the last column here. So we see that the marginal contribution to the model's maximum squared sharp ratio is 0.08 units. So if we include this factor here, it increases the maximum squared sharp ratio. Next, what we have here, we regress on the left-hand side, we have the size factor. Again, we are interested in what is the marginal contribution to the model's maximum squared sharp ratio. So what we do is we regress the size factor on the remaining factors, which is the market factor, the value factor, the profitability factor, the investment factor, and the momentum factor. So what we see is the intercept term is 0.48% per month. Yeah. The t-statistic of the intercept term is 4.35, which is highly significant, which means that 0.48% of the size factor here cannot be explained by the remaining 5 risk factors of the 6-factor model. So adding the size factor to the other factors here increases the mean variance frontier. So we also see is that the marginal contribution to the model's maximum squared sharp ratio is 0.034 units. And this is an interesting result, right? Because earlier research has shown that the size factor actually doesn't matter if you take it by itself, so to speak. But once we regress it on the remaining 5 factor of the 6-factor model, we see that there is a contribution. And how can this be explained? So it can be explained by the co-movement. Yeah? So there's some collinearity going on here. And because of some covariation, the size factor becomes significant after we control for the other risk factors. So the size factor could be meaningless if we take it alone, but if we have it in association with all of the other risk factors, it becomes obviously, it adds to the mean variance frontier expansion, yeah, which we see here. It adds to it increases the maximum squared sharp ratio of the model. So, and the same thing is if you go through the other factors here. Unfortunately, what we see here, the value factor, once we regress the value factor on the remaining risk factors here, which we see in this row here, in row 3, yeah, the intercept is 0.08, which is obviously very low, much lower compared to the other risk factors. What we see also is that the t statistic is 0.9, which indicates that the value factor, after we control for the other factors here, the value factor becomes insignificant. And this means also that this increase, or the marginal contribution to the model's maximum squared sharp ratio, which is 0.002, is insignificant, because the t-statistic tells us of 0.9 tells us that this point estimator of 0.08 is statistically not different from 0. So the risk factor, this HML, the value risk factor, can be fully explained by its exposures against the remaining risk factors of the 6-factor model. Yeah. So this is basically what we learned from panel A in table 5. And panel C, or sorry, in panel B, we only use small stalks. Yeah? So we use small stalks for implementing the value factor, the profitability factor, the investment factor, and the momentum factor. Yeah, and basically we see very similar patterns. And again, what we see is, okay, that the value factor here is the only factor, obviously, that does not add to expanding the mean variance frontier. So we see here is even negative, but not different from 0, because the t-statistic here of minus is minus 0.59, indicating that it's not different from 0. Yeah. So this is basically what we learn from table 5. Table 6 is not so important for our purposes. We can jump over that table. Table 7 is again quite interesting. We were discussing that a left-hand side approach might yield different results than the right-hand side approach. So depending on the test assets that you use, you get different test statistics. And this is also what we see here, yeah, for table 7. So here, for instance, in panel A, they use they have 260 test assets, and here in panel A, they use all of them. Yeah, so they have 260 equations, this model, that they basically then simultaneously estimate. The course using here in the first row, we see that they use the 6-factor model using small spread risk factors for value factor, profitability factor, investment factor, and momentum factor. Moreover, they use cash profitability. Yeah. So we see the corresponding GRS test, and I suppose this is an F test here, indicates 2.26. Okay, this is an F test, obviously. So the p-value is 0.000, which is obviously smaller than 0.05, indicating that this GRS test indicates statistical significance on any level, obviously. So, which implies that this 6-factor model here is not able to price all of these 260 left-hand side test assets simultaneously correctly. So it cannot price these simultaneously and cannot price them correctly at the same time. This is what we learn from this table here. So what we also see is, if we jump a little bit on here in the second last column, we see the maximum squared Sharpe ratio. So the maximum squared Sharpe ratio is 2.226 maximum squared Sharpe ratio. So if we move down, in panel A, the last row, we have the 6-factor model using operating profitability. The 6-factor model of equation 4, you remember. So the GRS test, what we see here, is 2.54. It's higher than 2.26. So as we see here, the GRS test increases linearly as we move from this model from row 1 to the last row. Okay, so obviously the best model, if we check the GRS test, even though all of these models here, as we see here, cannot price these test assets correctly, these 260 test assets, but what we see is, as we move from the first model here to the last model, the GRS test increases linearly. So with respect to the GRS test, because the first model here produces the lowest GRS test, we would choose this model here because it produces on average the lowest average pricing errors across these 260 models. Because this is what the GRS test is telling us. It gives us basically the average pricing errors across these 260 models. And if we now move here to the using the right-hand side test, here, what we see here, using the maximum squared Sharpe ratio approach as proposed in Fama and French, we see also the same patterns. The maximum squared Sharpe ratio decreases linearly as we move from the first model to the last model. So using a 6-factor model with using small spread risk factors and using cash profitability produces a maximum squared Sharpe ratio of 0.226. Using a 6-factor model that uses all stocks and cash profitability produces a maximum squared Sharpe ratio of 0.190. Whereas a 6-factor model that uses all stocks and operating profitability produces a maximum squared Sharpe ratio of 0.135. So the maximum squared Sharpe ratio decreases linearly from model 1 to the last model here. It's basically the same conclusion like we have here with using the GRS test. So in this case here, using these 260 test assets here would produce basically the same results, irrespective of whether we use the maximum squared Sharpe ratio approach or the GRS test. This is what we learn from table 7. So now here in panel B, they use different test assets. What you see here, 5x5 sorts on market equity and book equity to market equity, operating profitability, cash profitability, investment, and momentum. So they use different types of test assets here. And what we see here is, again, in the first column, we see the GRS test it's increasing as we move from the first model to the last model. So the conclusion is still the same. Okay, even though none of these models here is able to price these test assets here used in panel B correctly, because the p-value obviously indicates that the GRS test is statistically significant. Even though this is the major outcome, we can say that this first model here produces the lowest average pricing errors, because the GRS test here is of 1.99 is lower than the GRS test compared to all the other models here. The same conclusion we would arrive here using the maximum squared Sharpe ratio approach. What we see here in the second last column, we see also if we use these test assets here, as in panel B, we see that the first model here using small stock spread risk factors And cash profitability produces a maximum squared Sharpe ratio of 0.226. And the last model here, use the six-factor model using all stocks and operating profitability. Yeah, the last row in panel B produces a maximum squared Sharpe ratio of only 0.135. Yeah, and again, also here we see that the maximum squared Sharpe ratio linearly decreases as we move from the first model to the last model. Here in panel C, we see that we have a little bit, we have again different test assets here, what we see in the description of table C, but we see that also here that the GRS test is now gives us now basically the same results. Yeah. So again, we see that this first the model in the first row here using small stock spread risk factors and cash profitability produces the smallest GRS test statistic. And also, if we check the maximum squared Sharpe ratio, here we see that this model produces the highest maximum squared Sharpe ratio. Yeah. So we would again come to the same conclusion. This is important to know from this table. Then the conclusions. So what we know is, okay, what Fama and French recommend is, so if you compare different models, obviously one should keep the number of models low, because there's always the risk of data mining. If we use if you use 500 models, obviously you will always find something, but this is due to data mining, data dredging. So one should be careful which which models or which factors one includes in the search for a factor model. So this is all that we are interested in concerning this paper, choosing factors.